All right, and welcome to 4.3 relating gravitational field strength to gravitational force. So, one of the things that we want to learn today is to compare the gravitational field strength and acceleration due to gravity. Now, that sounds kind of redundant and about the same thing, but there's a few key differences that are happening here. So, we know from kinematics and dynamics and earlier in this course that we have that our gravity is equal to 9.81 meters per second squared. But we kind of just accepted that value from Isaac Newton and from the physics classroom and all the other things that we have here. But it comes from this idea of our two formulas for FG. So we know that FG is equal to mg. And then if we have two test values kind of equal to each other, so using our weight and then our Newton's law of gravitation. So we have Fg is equal to mg, then we have Fg is equal to g mass A mass B over r squared. And when we kind of use these together and put the two values together, and I'm distinguishing this MB to be different from just the mass. The other way that it's written in the textbook is that this is mass source and mass test. So that when these guys combine and work with each other, we're going to divide this one over so this one cancels. And that you have your gravity is equal to the universal gravitational constant multiplied by the source mass or the big mass over your distance r. So this gives you the 9.81 meters per second squared when this is the mass of the Earth. And this is the radius of the Earth. So that's just like a kind of cool overview of what's happening here. The other thing that we need to note is we have our gravitational field strength, which is a Newton kilograms. So gravitational field strength is 1 Newton kilogram, which is wild because we usually look at these things being meters per second squared. That's our acceleration. So if we remember this one being, let's change that G to an A actually. That's usually the units that we use it to, but newtons can be rewritten as kilograms times meters per second squared over kilograms. These guys cross out, and then you're just left with 1 meter per second squared. And I think that's one of your guys' concept questions too, so you're welcome. Then what I want to look at is an example with you guys. It is on page 218, number 4.5. Let me grab that question for us. So this example wants us to calculate the magnitude of the gravitational acceleration of an object at the equator on the surface of the Earth and the Moon, referring to a table given above. So that is also on the same page, but that table looks like this. Just in case you're wondering where the values are coming from. Now, to calculate the magnitude of the gravitational acceleration, this is telling us in A, to use our equation, G is equal to G m source over r squared. G Earth, I'm going to shorten that just to this, is equal to, and I'm trying to find Earth, so the G stays what we normally, 6.67 times 10 to the negative 11 Newton meter squared, kilogram squared, multiplied by our M source. So that would be 5.97 right here. All divided by r squared, so our equatorial radius, that is at the largest part of the Earth's. And this is fantastic because this crosses out, one of these cross out, and then you're just left with Newton kilograms, which is also meters per second squared. So that works out perfectly. We put this into our calculator, and we should get this to 3 sig figs, so it's 9.78 meters per second squared, or 9.78 Newton kilograms. Okay, and then we need to also do that for the moon. It's going to be the exact same sort of setup. So G moon is same constant here. The only time I ever write all my units for any question is when I'm doing questions for you guys. 10 times 6 meters squared. All of the same cancels happen, which again is lovely and exactly what we want. And this gets us to 1.62 meters per second squared, or 1.62 Newton kilograms. Okay, and then it wants us to find the ratio of G Earth to G Moon. So when we're setting up a ratio, I'm actually going to put it up here. It told us how it wants it set up. It wants it to be G Earth over G Moon, which gives you 9.78. And I'm dropping units because a ratio is a unitless form of measurement that I know I don't need to worry about that stuff. And you can do the same, or you can show that you understand that canceling by setting it up and then canceling it, which gives us 6.04. And then it asks what that ratio means. That ratio means something very cool. This tells us your weight is about 6 times less on the moon than on Earth, which is kind of neat. Then I want to go over another example here with you guys. It is 4.6 on the following page. This one asks, what is the mass of a 60 kilogram student on Mars and Earth? What is the student's weight at the equator on the surface of Mars and Earth? Use the data, da-da-da. So the first thing that we need to do is G Mars. G M over R squared. And at this point, I'm going to start dropping the units because I've written it twice for you guys, and we know what we're supposed to get up here. Remember, this unit comes from the table. And so is this one. And to 3 sig figs, this gives us 3.70 Newton kilograms. And we're leaving it like this, that it is a Newton kilograms because we're worried about the mass, not the acceleration. And then for Earth, same setup, very similar values. Oh, whoops. Wrong value written there. So 6.38 times 10 to the 6th squared for 9.78 Newton kilograms. Fantastic. Then what we are looking for is our F-grav, or your FG, sorry. Because this is where we get to use our mass, and this is the mass of the student, multiplied by the gravitational constant of Mars, which we found up here. So then this is 60.0 kilograms multiplied by 3.70 kilograms. And then for the FG, Earth, mass gravity of Earth, and then multiply that by 9.78 Newton kilograms, 587 newtons. Now, you may have noticed that we kind of drove by A, didn't really talk too much about it, and we were like, okay, cool, let's just do what we need to do for B. What we need to realize about A is that A tells us mass versus weight. Now, mass is a scalar quantity, so it's going to be the same, which is kind of neat. So we didn't even really have to do anything. So this just means that this both would be 60 kilograms. But weight is a little different because it relies on gravity. And the funky thing too is for a long time, we thought that the gravitational field strength was a constant at any location on Earth. But it's actually different. And there's a simulation that you can test out and you can try if you are interested in it. But the kind of gist of it is that depending on where you are on Earth, it's different. It depends on altitude. So how do I want to say this? The value of G depends on altitude and latitude. So if you are towards the equatorial plane, you are going to experience less G, but the value of G increases as you move towards the poles. And this is because Earth is not a perfect sphere. It's slightly flatter at the poles and bulges slightly at the equator. Like it's more of like a kind of like an oval. It's about 21-kilometer difference too. And the farther the object is from the center, the smaller the value will be. So the G value is less at the equator. It's the smallest, and it's because you're the closest to the center. I would recommend pausing and stopping here, but you are also good to keep going if you are interested in what we're going to do next here, because the next part of what we're doing here is the idea of true weight versus apparent weight. And this kind of ties into some of those things that we were just talking about. When we're dealing with true weight, it's the gravitational force acting on an object that has mass. So that's kind of like when we are looking at all these different masses, this is when we have to use our FG of an object. And this is measured on a scale when the object is at rest or traveling at a constant velocity in the vertical direction. And that's because we know that F net is going to equal 0 in that equation and situation. And then we can find that magnitude of the normal force in order to figure it out. And that looks like this. Fn is equal to mg. Very similar to the equation that we just used. But if, excuse me, situations where a person is accelerating in the vertical direction, so if you're like in an elevator and accelerating, the scale's not going to give the same weight reading. It's going to give the apparent weight of the object, which is the negative of the normal force. So the apparent weight deals more with this equation here. And then if the elevator were accelerating down, you would still use this equation, but you would expect the person to feel lighter. So if I was 50 kilos and I was accelerating down, I was sitting on a scale, that weight would be different because I would kind of be operating in the opposite way. And if that cable snapped and you went into free fall, we would be weightless because the Fn, so free fall, is the apparent weight, which is all equal to 0. Now, you're probably thinking about, well, what about people in space? They float and they must experience weightlessness. It's a great thought, but it's not exactly true. The apparent weight is still 0, but they still actually experience the force of gravity. It's just less. So the scale reading would be 0 just because the ISS and everything is free fall, but that person is not in free fall. Sounds confusing, but let's look at an example and kind of get some numbers happening here. This is on page 224. A 100-kilogram astronaut in a spacesuit is standing on a scale in a rocket. The acceleration of the rocket is 19.6 meters per second squared up. Calculate her true weight and apparent weight during liftoff of Earth. So, to find the true weight, Fg is equal to mg. True weight is equal to 100 kilograms, negative 9.81 meters per second squared. And it is negative because the acceleration, the Fg, is acting downwards from this person. And our normal force is acting upwards. So negative 9.81 times 10 to the 2 newtons. Okay, now for the vertical direction, write the equation to find the net force. So F net is equal to the Fn plus the Fg, which tells us mass, acceleration, Fn plus Fg. So then we have Fn is equal to mass, acceleration, minus Fg. This is the acceleration of the rocket here. That's why we have to do more than one step here, is because we're not just calculating her, we're calculating the acceleration of the rocket and how that plays into her weight as well. And this is going upwards. Okay, and then to find the apparent weight, we have the weight, the apparent weight, is equal to this idea of the negative Fn. And that is because of how we get to this equation. I can kind of explain that a little bit better here, is that when we have this setup, this becomes negative ma minus g, which gives us that mg minus a setup. They just kind of work together here. So the apparent weight is the negative of our normal force here. So our normal force was 2.94, so this gives us negative 2.94 times 10 to the 3 newtons. This is down. Okay. And then just to kind of tie it all in together, talking about free fall in weightlessness, if you read through the chapter, it will make a little bit more sense to you. But if we're always talking about the space science thing, it needs to be far, far away from the gravity of any celestial body with zero acceleration, and then they will experience true weightlessness. Everything else is going to be this idea of apparent and then true weight, but it'll never really be when you're on Earth or around Earth, because you'll have that force of gravity acting on you. It's like if you looked at 4.8 and it wants to talk about true weight and apparent weight in deep space, the mass is still the same, but the gravity is negligible. There is no gravity. So your F net would equal your Fn in that case, and it would be a pretty easy solve from there. Past that, I think that wraps us. That should be the end of the chapter. Remember, this should take 2 days. Break it up into 2 days so you can have some time to kind of comprehend and debrief everything. Good luck, and let me know if you have any questions.